Hello, Huang Shao.
Yeah, I've seen him.
Okay, can you hear me?
Yeah, right. Okay, that's great.
Great. You can start sharing screen and I'll give the introduction.
Sorry, I couldn't share my screen, so maybe you should set me as a,
Oh, okay.
yeah, give me the authorization, yeah.
I'll make you co-host.
Oh, okay, yeah, co-host is great,
Right.
yeah.
Awesome.
Right, all right, let me share my screen. Okay, so could you see me, see my screen? Yeah.
Yeah, we
Yeah.
can.
Okay, that's great.
All right. I am pleased to announce that we have Hongchao Li from the University of Tokyo giving the quantum theory seminar today. So Hongchao is a PhD student working with, in the Department of Physics, working with Masahito Ueda. His research mainly focuses on Yang-Li theory of quantum phase transitions, quantum many-body physics of open quantum systems, and quantum algorithm and complexity and physics of deep neural networks. All right, without further ado, take it away.
Okay, thank you very much for your introduction. So, yeah, let's start our seminar today. Yeah. Okay, thank you very much. Yeah, so today I'm going to introduce my recent work on optimizing digital quantum simulation of open quantum systems. I'm Hongchao Li from the University of Tokyo. So this is the archive number, and my collaborators are Xihang Yu, Ignacio Sirac, and Rahul Trivedi in the Max Planck Institute. Okay, so let's now first introduce the background of our work. So our work mainly concerns a problem like a Hamiltonian simulation problem, which is one of the central problem in the quantum computation and the quantum simulation. The problem is, given a description of the Hamiltonian and the evolution time t, how to perform a unitary evolution e to the minus ith up to some error, epsilon. So the idea to use a quantum computer is because a quantum computer can simulate the Hamiltonian very efficiently if the Hamiltonian is local. And upon some measurement, it can efficiently answer questions that a classical one cannot. For example, as we know, like Shor's algorithm and the Grover search algorithm. The first initial idea of the to use the quantum computer to calculate the classical problems was raised by the Richard Feynman. Yeah, and one of the very well-known methods to calculate to do the quantum simulation is the trotterization, or we also name it as the product formula. So given target system where the Hamiltonian is composed of some Hj, so some small local Hamiltonian acting on some local sites in the system, and also each Hj has a bounded norm. Yeah, so given such a summation of the such local Hamiltonian Hj, so how do we simulate it? And one of the good method is to use the Lee-Trotter formula given by this one. So just to take the product of all the factors in the e to the minus ith, and the difference actually is bounded by this one. So if the t is small, then we can say it's the error is to the second order. However, this method can be also generalized to two-case order by the Suzuki formula. So before introducing the Suzuki formula, so let's introduce how to realize a long-time evolution, the simulation of long-time evolution when t is very large. So the first thing we need to do is to chop the time into r steps. So where in each step we have a t over r, for a time evolution. Where if we take r very large, then t over r will be small for the time evolution. Then we can use the Lee-Trotter formula to get close to the full evolution of the Hamiltonian. And the error is given by this one. And by repeating r steps, we get the simulation for the full Hamiltonian, even for a large time t. From the error estimation, we can see it decays power in the power law of the steps r. Then if we take the infinite step for a simulation, yeah, then this error can be effectively reduced. To achieve some accuracy epsilon to simulate the full Hamiltonian, it suffices to take R equals to this order, nt squared over epsilon. So this gives the gate complexity n squared t squared over epsilon. However, this is not enough because n squared t squared is still so large, especially for the long-time evolution and many-body quantum many-body system. So we still need to improve this gate complexity. Then we need to generalize the Lee-Schroeder formula to the two case order. And we reorder the Hamiltonian terms in the even odd pattern. In other words, so we first assume that the Hamiltonian acts on the nearest neighboring states, like HII plus 1. So then we regroup them into this way. So like 1, 2, 3, 4. So we regroup it as H odd. Well, for the other groups, we regroup it as H even. For these two groups of Hamiltonian, they do not commute with each other in general. But for each Hamiltonian in the one group, so they commute with each other. So then we can use the two case order product formulas given by this one. So we first approximate the full evolution by the S2T. So with the H odd and H even to decompose it like in this way. Then we can use the S2K minus 2 to derive the S2K such that the error can be controlled in this way. So which is proportional to T to the 2K plus 1's order, where the PK is given by this one. So this full formula was introduced originally by the Suzuki in this paper. Yeah, when the K is very large, then we know, yeah, if we take the time delta T to be small, then yeah, this error generally vanishes if we take the time slices to be very small. And finally, we get this gate complexity, which actually decrease with the increase of the number K. So if we take K goes to infinity, we can reach nearly linear scaling with the N and the T here. So this exponent will vanish.
Hongqiao, one question. Can you hear me?
Please. Okay.
Yeah, can you back up a bit? So, you said that H odd and H even generally don't commute. I thought they were just the same Hamiltonian divided into different pieces.
Yeah. So yeah, do you mean this one? Divided in pieces?
Yeah.
Okay. Yeah. So this is assumption. So originally we need to assume that the Hamiltonian is local. Then we can do the effective, efficient and effective simulation.
So what is the difference between H odd and H even?
Sorry. H odd is for the first group and H even is for the second group. So they do not commute with each other. But for each Hamiltonian in one group, they commute with each other. So that's our requirement.
So why do they not commute? Are they realized by the same Hamiltonian, or are you doing some like circuit evolution or something?
Yeah, we are doing some circuit evolution. For example, please check this one. So S2T. So we need to do some circuit evolution for each independent Hamiltonian. So for example, H12 acting on the sites 1 and 2, and H23 acting on the sites 2 and 3. So H12 and H23 generally does not commute with each other. Yeah. Sorry. So here 1, 2, 3, 4. So this number indices representing the sites they are acting on. Yeah.
I see.
Yeah. Yeah. Thank you for your question. Yeah. Okay. So if we use the Suzuki formula to a very large K, then we can realize nearly linear scaling of the quantum circuit gate. Then I need to introduce the motivation why we study the trotterization. The product formula algorithm is an ancilla-free algorithm and is arguably the simplest approach to the quantum simulation. Even though there are some other methods like ancilla to use the ancilla qubit or quantum signal processing, yeah, this is still the most powerful one to simulate the quantum unitary evolutions. Yeah, product formulas are surprisingly efficient in practice, especially compared with the quantum signal processing. So which usually is difficult to make a very large scale simulation. Product formulas can exploit the commutation of Hamiltonian terms to speed up the simulation. And also there are some other approaches as I mentioned, but compared with the trotterization, this is more practical one to be realized in the experiments. Yeah, then let's move on to the real systems. Above, the analysis is only restricted in the closed quantum systems. However, the real systems inevitably suffer from the dissipation. So many systems have dissipation, such like particle loss in ultra-cold atomic systems, and also the coupling to the external bath in the condensed matter physics. So we usually have such dissipation both in the condensed matter systems and also in atomic systems. So then our one natural question is how to simulate such an open quantum system. In usual cases, we can always write our total Hamiltonian like this way. So the total Hamiltonian is composed of the system Hamiltonian, environmental Hamiltonian, and also the interaction between the system and the environment. Then by tracing out the environmental degrees of freedom, we have the evolution in the system behaves in this way. This is known as the Nakajima-Zwanzig equation. Here the L in the equation represent the Liouvillean operator, the commutation between the operator and the total Hamiltonian. P and J here represent the projectors onto the subspaces of system and environment. This equation is typically very difficult to simulate in a classical computer, because here we have an exponent here in the integral. In the real simulation in a classical computer, we have to do the Taylor expansion to this exponent. But if you do the Taylor expansion, it doesn't guarantee the positive semi-definiteness. If we expand it, so which leaves a great difficulty to simulate dynamics of the Nakajima-Zwanzig equation on a classical computer. So that's why we need to resort to the quantum computer for the simulation. Furthermore, if we add some more assumptions, the first one is the Born approximation. So which states that the total density matrix can be always decomposed into the product in the whole dynamics. So which means that the total density matrix can be expanded like a direct product between the system density matrix and the bus density matrix, and additional terms can be ignorable. To realize this approximation, we need a very weak coupling between the system and the environment, or a very small dissipation rate. Secondly, we need a Markov approximation, which states that the evolution equation of the density matrix is independent of the density matrix before the time t, which means that the evolution equation of density matrix only depends on the density matrix at the time t. We ignore all the correlation between this density matrix and at time t and before the time t. If we assume these two approximations, which means that we have a weak coupling between the system and bus. Also, the relaxation time, or the correlation time in the bus is very short. Then we can further simplify the Nakajima-Zwanzig equation as the Lindblad equation, which is given by this one. So Li represents the Lindblad operator, which acts on the system. There are some examples for the Lindblad operator for spin systems. One example is the dephasing noise. So L equals to sigma z, and also damping, L equals to sigma minus. So these two types of the noise are very common in the atomic systems and optical systems. Okay, so that's the background. Now we move on to my the context of my work. So is there any question? If not, I'm going to move on. Okay. So above is the motivation and the background. So now we have stressed the importance to consider simulation of open quantum system. Then how to do the simulation of open quantum system? Okay, so we begin from a non-Markovian simulation by assuming the following points. So later I will explain why we first consider non-Markovian dynamics instead of a Markovian dynamics, which seems to be simpler, but it turns out to be even more difficult to simulate. So to simulate the non-Markovian dynamics, we need to assume two things. So firstly, we need a linear coupling between system and the bus. So here linear by we mean that so the interaction Hamiltonian between the system and the bus only contain the first order of the bosonic operator. It shouldn't the coupling Hamiltonian or interaction Hamiltonian cannot appear like a quadratic or even higher order terms in the bosonic operators. It can only shows up one boson annihilation and one boson creation. Secondly, we need a Gaussian bosonic bus. Gaussian bosonic bus, we mean that the bus Hamiltonian should be a quadratic form of the bosonic operator, like A dagger A. So the total Hamiltonian is given by this. So where system Hamiltonian is a local system Hamiltonian, which acts on the which is composed of the local Hamiltonian acting on only the nearest neighboring sites. Secondly, we need the interaction, so between the system and the bus. So please take a look at this large AI. So which is the coupling between the system and the bus. So this acting on the bus, the bus Hilbert space. But here actually it does not only depends on the time t, but also depends on the previous time. So it means that so at the time t, the Hamiltonian concerns not only the bosonic operator at the time t, but also in the previous time. Yeah, and also so initially we also assume that the system density matrix and bus density matrix are separated. And also in the following, we mainly assume that the initial density matrix for the bus is vacuum state, where no bosons at the initial state. The bus actually, we assume it to have such a property. So the correlation function or the memory kernel is what we call the Ki T1 minus T2 here, which only depends on the difference between the time of two boson operator, and it's a local correlated system. Sorry, a local correlated bus. Yeah. So in this case, to proceed with, we still need to make some assumption on the this memory kernel here. So firstly, we need to assume it's always finite, and then the integral of the such a memory kernel is bounded, which is useful in the following proof. Yeah, so here you can but it's usually satisfied in the non-Markovian setups. For example, Ki tau is usually to be assumed as a Gaussian decay-like function, which satisfy these conditions.
I have a question. So
Yeah.
usually I thought the utility of making the Markovian assumption when people go that route was the fact that you have a finite memory, like the interaction with the bath dissipates fast enough that you can derive this like effective evolution in a much more easy fashion. And it seems, so can you explain to me why having this finite memory kernel doesn't like violate your non-Markovian property?
Yeah. So that's what I'm going to explain in the following slides. Yeah.
Okay.
So why we need a finite memory kernel? Yeah. So the evolution. So actually it will be explained here. Yeah. So okay. So the evolution of the density matrix here is given by this. So we use the total evolution we use the evolution for the total Hamiltonian. Then we trace out the degrees of freedom in the environment, to get the evolution for the system density matrix. So if the memory kernel satisfies this delta function, then we recover the Markovian Lindblad equation. So as Tamara mentioned. So this is the Lindblad equation. So Lindblad equation breaks the assumption before. So so that is unbounded. So that's why we need to introduce this in the next section, and I will explain why it's difficult. So through the by assuming the form of the evolution and also the memory kernel, we can prove the following theorem. So theorem, if the coupling Vi is a smooth function of t, which decays super polynomially. So this two condition means that Vi is smooth and it decays faster than any polynomial way. Then the channel epsilon st can be simulated with an error with this amount of geometrically local gates. So Vi appears here. So it appears in the coupling between the system and the bus. So it means that how many bosonic modes we involve to construct a coupling. And usually, so we know that it should decay very fast. So it shouldn't depend on should not depend on so many bosonic modes other than at the time t. Yeah, and so the difficulty to prove here is that there's no bound of the norm for the local Hamiltonian because of the bosonic operators, and also the bosonic modes are infinite. Since here we have an integral of the bosonic modes at different time, which means that S is actually a continuous quantity. We have an infinite bosonic modes, which is impossible to realize in a quantum simulation experiment. And so okay, so so if we want to see how to prove this point, we need to know how to construct such a unitary evolution by a chautorization method. Then we can know how to bound the difference between the real evolution and our proposed evolution.
May I ask
So
a quick question regarding the
please.
condition that you show in the previous slides?
Please.
So there's an upper bound on a derivative v, but I presume v itself has a theta function looking thing, right? Because you cannot have the photon coming from the future to influence the state of the system. So v itself look like there must be a step function already involved. So does that make the derivative big?
I understand meaning. Right. So in our models, actually we assume it's symmetric around the time t. So maybe this assumption is a little vague.
Or am I right? Because I mean, I thought, like you cannot have a photon coming from the future to influence the state of the system, right?
Right. So so here this assumption is a little so actually when we read the paper we want to avoid this. Actually, you are right. So it only involves the photon in the past. So here this derivative is for the for example when S is smaller than t. So we don't assume that any properties at the time, just at the zero.
Okay.
Thank you for your question. So this property is only for t when t is larger than zero.
Okay.
Right.
Thank you.
Okay. So okay. So then we are going to show the skeleton of the proof by constructing such a chautorization method. So to construct the whole unitary evolution, so we still need to chop the time period into some slices. Namely, here we use the large T to represent the number of the circuit depths or the number of the chops we need to prepare. And then we take the direct product of this short time evolution. And for each short time evolution, so for namely in the delta T, so we need to use the evolution on the odd side or even side as we organized before in the Suzuki formula. Then our method is only to use to only construct this one. But actually this is constructing the Suzuki formula. And by following the exactly same evolution constructed in the Suzuki formula, finally we have this quantum channel we propose to construct. And the only thing we need to do is to estimate what's the error between the chautorization method we construct and the real quantum channel evolution. As I mentioned before, the difficulty is here we have an infinite number of bosonic modes. And also for each bosonic mode, the boson number is unbounded. There's there is not a norm upper bound for the bosonic operators. So then our strategy is like this. So firstly, we need to discretize the bosonic modes in the time domain. Secondly, we need to bound the boson number for each mode. Finally, we do the chautorization to realize our final goal. Okay, and this is the scheme for our basic strategy. Okay, so so firstly we need to chop the time period into some slices, with the wise eta. And then we use to discretize. We use the truncation to truncate the boson number for each bosonic mode. To realize it. So then we mentioned firstly, what's the discretization? So here we have a continuous function vi t minus s here. So we need to decompose it as a Legendre polynomial. So for example, we chop it into many slices. And for each slice, for one slice, for example, from the n eta to n plus 1 eta. So we can decompose it in by the Legendre polynomial. So where this Legendre polynomial only lies between the n eta and the n plus 1 eta. Then finally we can rewrite the bosonic modes like a summation of this bosonic modes. So where we redefine the BIGN as a bosonic mode, which also satisfy the commutation relation of the bosonic modes. In this time period. Then for this BIGN, so our idea is, so here we have an infinite number of the bosonic mode BIGN. So we need to truncate it as this one. So for the given time period between the n eta to the n plus 1 eta, so we truncate the modes. At most, there are J-max mode of the bosonic operators. Okay, so by truncation we need to estimate what the truncation brings to our to the error of the simulation. So to estimate it, we need firstly define a new memory kernel for the discretized bosonic modes. So by this one, so we just use the truncated bosonic operator defined here, not this infinitely sum one. So this one is truncated one, and we can prove that. So the truncated memory kernel, the difference between the truncated memory kernel and the original memory kernel is bounded by this quantity. So where djmax plus 1 is assumed to be a O1 constant, so we can see it decreases very fast with the Jmax. So it means that we don't need to set Jmax to be very large. And also we can bound the integral between for the difference. And finally, with this integral, with this two inequality, especially this inequality for the integral, finally we can bound the difference between the original quantum channel and the discretized quantum channel we design. So it's bounded by this one. So it's proportional, linearly proportional to NT, and also a factor which is proportional to the eta to the J max plus 1's power. And R here is a O1 factor. So this means that we need to design the eta to be small. If the Jmax is a finite value, or especially an O1 value, so we need to bound the eta to choose the eta to be this quantity, so which should be small. If we take Jmax goes to infinity, actually eta it can be also chosen as a O1 factor. So the first step is the discretization. And the second step is to bound the boson number in the dynamics. In general, this is very difficult. For example, if we start from arbitrary initial state, it's very difficult to bound the boson number in the dynamics. But if we begin from a vacuum state, this problem becomes very simple. We can prove such a lemma. For an intermediate time tau, the state psi tau satisfies this condition. So here psi tau means originally, so the system and the environment also, they both are in the pure state. So here psi tau means after a tau time evolution. So we have this inequality. And here PIJND means projection on to the subspace with less than d boson or d particles. And from this inequality, we can see that the probability to emerge more than d bosons actually exponentially decays with d, the boson number. It means that it's very unlikely to emerge more many bosons. Then we can safely to choose a number to truncate the Hilbert space. then each bosons can be considered as a D-level system, which is much easier for us to analyze and bound the difference between the original quantum channel and this quantized, so some QD-tized, quantum channels.
Question, do you have
Yeah,
any
please.
intuition for why that bound doesn't depend on time at all? Because I would imagine since you have a finite memory, it would care about that.
So that's a very good question. Yeah, because here we add some assumptions on the memory kernel. So firstly, it's if once we assume that the upper so the maximum value of the memory kernel is bounded and the integral is also bounded, then we can prove it. If this is some delta function or the integral is not bounded, then we cannot reach the same conclusion, this conclusion.
Okay, so shouldn't it depend on that bound at the very least?
Yeah, right. For example, if your memory effect is very strong, of course, it's possible to have many bosons emerge from the environment. Yeah, so we need such an assumption.
So does M enter the bound in the expression you just had?
Yeah. So some bounds in the actually here the C0 depends on the M actually.
Okay.
Yeah. So it enters the system, or you can consider from some smoothness of the VI. Yeah, so that they are somehow equivalent to each other. Yeah. Right. Okay. So since it's very unlikely to emerge many bosons in the environment, so then we can truncate the Hilbert space for the environment. Yeah, by this way. So we just do the projection on the environment on the interacting Hamiltonian. So here we use the interaction picture to absorb the bus Hamiltonian into the operator here. So for the large AI, yeah. So we don't need to consider the environmental Hamiltonian. Yeah, by projecting the Hamiltonian for the old Hamiltonian and the even Hamiltonian, so we finally have this two projected Hamiltonian, and we can estimate the difference between this projected quantum channel and the original quantum channel, and finally we reach this conclusion. So by looking at this error bound, we can see the error actually exponentially decay with the D we choose. So in other words, we can just choose this D, so which scale logarithmically with the n square and t square. So this is very good news that even for a very large n and d and the t, so we don't need to choose a very large d. I mean the linearly scale with the nt. So logarithm one is good enough. Okay. So finally, we just need to assemble all the results we have obtained together. So finally, we need the total circuit depth as before. But please remember that here the Hamiltonian norm is still not estimated yet. So we still need to estimate the norm of the Hamiltonian, which may depend on the time and the size of the system. So the norm of the interaction Hamiltonian is given by this. So it's bounded by this norm. And finally, if we want to estimate the total circuit depth, additional to this chortlerization circuit depth, we still need to time this one. So to get the real total circuit depth, because usually we need to estimate the in the previously we mentioned that for the chortlerization method, we need the local Hamiltonian to be bounded, which is less or equal to 1. But here, this actually scales with the size n and the t, so we need to retime it here. So finally, by choosing the large p equals to 2p, so here the small p is exactly the k we defined before, and also by choose the maximum mode of the maximum number of the bosonic modes as the p. So finally, we get the such a circuit and the elementary gate complexity. So the circuit is exactly the same as the Suzuki formula, and also the elementary gate complexity is also the same as Suzuki formula.
Question?
Yeah, please.
All this is kind of new to me, and I would appreciate being able to frame your result in a sort of a larger, I don't know, established context. So when you say elementary gate complexity, what does that mean? Like
you
in
mean
terms of, like, so does that relate to how many qubits the gate has to involve, or like, can I think of this estimator and bound in practical terms?
in practical terms, yeah, so our assumption is that the Hamiltonian of the system is geometrically local. So like
Yes.
yeah, this one.
Yeah.
But if you're acting on some O1 qubits, you can regroup the system to realize some nearest neighboring interaction.
And so I understand local Hamiltonian, but you gave an expression for gate complexity. How am I supposed to think about that?
Oh, you mean the meaning of the gate?
Yes, yeah.
Oh, so this means that how many how to say geometrically local unitary circuit you need to implement such a quantum channel.
How many gate types you need? Is that a way to think about it?
Yeah, right. How many gates? Local gates. Yeah.
How many different local gates I need? Is that what that's estimating?
Yeah, right.
And the circuit depth is for that many local gates, what is the depth that you need?
Yeah, right. So you can see, for example, like the picture I showed before. So this one. So along the x direction is the number of the sites, and along the y direction is the depth of the circuit.
Right.
So yeah. So by the product between the size and the depth, then you get the total gate complexity.
Mhm.
Yeah, it means how many gates in total you need to use.
So it sounds like the mission of this paper, the work is to establish the equivalent of Suzuki-Trotter for open quantum system. Is that right? Is that what they're trying to do?
Exactly.
Uh-huh.
Yeah, exactly.
For
Yeah.
Suzuki-Trotter, there is the established like bounds, or if you want to get error below something, this is what you have to do. And that you're trying to do that for open system.
Yes, exactly. Yeah.
Okay, so
Yeah.
then I have a question.
Yeah.
Suzuki-Trotter is established, and you're trying to
Yes.
do this for open system. But for
Yes.
the established case, what is
Yes.
the state of art in actually implementing this on a physical hardware?
Yeah, exactly. That's
No?
a very good question. Yeah. So to implement the Suzuki formula, so we need this critical condition. So
Yeah,
the local Hamiltonian norm should be bounded.
uh-huh.
Yeah.
And
However,
yeah,
yeah.
uh-huh,
Yeah, in our case, so this boson spin interaction is unbounded.
uh-huh.
Yeah, which
So
leads to the breakdown of the
no, I
original.
understand why you're doing this theoretical work. I am asking a different question.
Oh, sorry. Yeah, please. Yeah, could you please?
My
share?
question is, where does the field stand, say, in implementation on physical hardware, going after, dynamics with trotterization?
You mean the how to implement such a
Experimentally, yeah,
experimentally? Okay.
yeah,
Yeah. For if we have a local circuit gate, for example, like such a local circuit gate, we can use the Tweezer array to implement the unit the most fundamental like a 2-qubit circuit gate. So for those if we use the trotterization for VO and the VE, so they can be decomposed into some single 2-qubit unitary circuit gate. So which can be implemented by, for example, like Tweezer array in a quantum platform.
so what I'm asking is, if you know, maybe this is not something that you've thought about, what's the actual status of the field? Like, who did what kind of experiment implementing trotterization to get dynamics for how many seconds? Can you give us that?
Maybe another way to rephrase that question is the Suzuki-Trotter formula gives a theoretical limit on the error, the lowest
Yes.
error you can get for a certain number of steps. But can we actually achieve that? How close can we get experimentally? How close have people gotten to that?
I
Uh,
estimate experimentalists will have to learn your work.
I see. Oh, okay. I understand your
How
question.
many
Yeah.
years from now? 5 years, 10 years?
Yeah, very good question. Yeah, actually, yeah. So I don't know, what's the real time to realize the such a simulation. Yeah. But I think it's basically the same as the time in the closed quantum system. So for example, if you realize in the milliseconds, so this is also at the millisecond levels or something like that. So in the real time, yeah. I'm not sure if I correctly understand your question. Yeah. So
Well, I guess for a real quantum simulator, you have to estimate the interactions of this quantum simulator, and the inverse of this interaction will serve as the time unit for the real quantum simulator, and such that you will estimate how many time periodicity according to this interaction, and that is the correspondence of the formulated opportunity for the real experiments. Just like for the real Lindbergh atom simulator, you have some interactions like
So,
MM
no, I understand the principle. I'm asking like in the units of real number. I don't know.
Yes.
Yesterday, the Minister of Science and Technology of Korea was asking, should I invest in data center or should I invest in quantum computers? When will quantum computers solve, something? So, it's a hard question. I was just kind of curious because you're thinking a lot about dynamics, simulation of dynamics. I was curious, what is the state of our thought?
Oh, so do you mean you want to ask if you want to simulate
Then worried about the power consumption of data center. He was wondering whether quantum computer will make it cheaper.
Yeah. I think it depends on which task you want to deal with. Yeah.
So so I'm trying to know, I want to know what task when can
Yeah,
we do
yeah. I
it.
think
I'm sorry, I distracted.
please.
But go ahead. Yeah. I was
Yeah.
Go ahead with
For
your
the
thought.
simulation, for the simulation of the quantum states, I think definitely quantum computer is deserve to be investigated, but invested. But I think it's a question that how important is to simulate an open quantum system.
No, I think simulating, if you can simulate dynamics, it is important. The question is like, can we
Yeah.
reach meaningful results? Like, what is meaningful and what do we need in order to reach each of them?
Yeah, I see.
That's the high stakes question.
Right. Yeah. Yeah,
But
exactly.
please continue your talk. I'm so sorry.
Thank you very much for the question. Yeah. Yeah, so above, we have estimated total gate complexity to simulate the whole many-body density matrix. Yeah, for the whole evolution. Yeah, so however, actually in the real situation, so we usually concern about the local observables instead of all the difference between the total density matrix. So is it possible to simulate the local observables with even less circuit complexity? So here I mean the local observable is something like this. So the average local observable. So between the local observable under the evolution of the real quantum channel and the local observable under the evolution of the choterized, I mean the designed quantum channel by us. So here the OX is the operator which only lies on the region X, and the rho S here should satisfy the trace norm equals to 1. Yeah, so our goal is to bound the error delta local with our designed simulation channel within an accuracy delta by the choterization method, where the circuit depth is independent of the number of sites. So this means that for our goal is to for example, if given a very large system, but the t is very small, the evolution t is very small. Then if we want to observe some local observables, not for the many global observables, then could we get an even less circuit complexity, which is independent of the very large size system of the system. The intuition to investigate such a problem is due to the Libres-Mon. or the locality of the quantum system. So yeah, let's review the Lieberman firstly. So Lieberman means that so the error can be error between the two average of the operators can be bounded by this factor. So here this difference means that the difference between the operator under the evolution of whole Hamiltonian, or the evolution of the local operator under some truncated Hamiltonian, where this XL means the set of sets that are within the distance L from X. Yeah, for example, yeah, if we consider a operator, so if it's due to the locality, so the propagation is only within this light cone, which means that the operators outside this light cone, has basically commute with the operator at the region, after the evolution of time t. So it means that there should be basically no difference to simulate the dynamics of the operator OX by a full Hamiltonian or a truncated Hamiltonian only within a given region. So here the L means that the propagation length that in the dynamics. So so actually Lieberman tells us that so this difference should exponentially decay with the distance L, or the size of the propagation, and also exponentially increase here with the time t. But this is just an upper bound. Yeah, so in reality, we will not exponentially decay always, exponentially increase always. Yeah.
So I have a question about that. So the locality helps you for early times, but once you reach thermalization time, when your operator has spread to the size of your entire system, I would imagine you no longer can take advantage of this to get lower complexity. Is somehow the fact that you have finite memory, like as opposed to infinite memory, that assumption going to help you out, or are you going to only be looking at early times?
That's a very good question. Yeah, actually, this bound, even for our setup, holds for the whole time. We have some assumptions. So firstly, as you mentioned, is that finite memory. So here.
So that means you will forget after some certain amount of time, so you can
Exactly.
essentially take advantage of the locality starting from that.
Yeah, exactly. Yeah. Also, we also rely on this Gaussian bus. If it's a non-Gaussian bus, we cannot bound it. Yeah, there's no Lieberman at all. Yeah. Yeah, so this Lieberman for the open quantum system for our setup has been proved in the previous paper. So this actually this result is exact for the for all the time t and the distance L. Yeah, and it's not only for the early time.
Maybe a quick question, just
Okay.
a clarifying question. So there was assumption about the memory kernel K, and then there's also a assumption on the Bath Hamiltonian. Are the two like really talking about the same thing, or because if I really say that the HE is this, then it comes with its own K, right? So because the dynamics of the Bath is driven by this HE alone.
But HE here, so here HE actually how to say so we didn't define any. So for example so in the in the evolution time it's not so this for example here AT here we mean is in the Heisenberg picture. So in this words in other words, so actually VSE here, so the V also enters the K here. So it's not solely determined by the Bus Hamiltonian. So it also depends on the property of V here. Yeah, so actually here the V and the spectrum of the Bus Hamiltonian together satisfy a condition. Yeah, so then we move every properties into here in the function V here.
Mm-hmm.
Yeah, so here the K actually depends on the V. Yeah. Thank you for the question.
Nice. Thank you.
Okay, so based on this Lieberman or locality in our setup. So in our setup, we require firstly the bus is short-time correlated. Secondly, the bus is Gaussian bus. Thirdly, we require the initial state to be a vacuum state. Together with these three conditions, we finally can derive the total error for the local observables, which is consists of these three terms. One is the first one is trotterization. The second term originates from the discretization. The third term originates from the qubitization. To control the total error within the accuracy delta, so we choose the short eta delta t for the time periods and also the d here. Okay. So please, so please remember that. So here delta t is firstly to chop the t into some slices, large t slices, and the eta is to further chop the delta t into delta t over eta slices. Yeah. So we need to chop the time by twice, and d is the upper bound for the bosonic upper bound for the boson number in the bosonic mode. Yeah, actually, yeah, compare with the previous results. Yeah, we will compare later. So we can see that it's nothing but to replace the n with t to the d's power. And in this case, the total circuit depth scales as in this way. So, and this, yeah, what I want to emphasize is this does not depend on the system size n. It only depends on the evolution time t. Okay, so the below is the skeleton of proof. But the proof is actually very tedious. So I will only show the error analysis of the discretization as an example. So for the other cases, they are basically the same. So to utilize the Lieber's amount, so we need to introduce some truncated Hamiltonian in the error estimation. So for example, now we want to estimate the error between the local observable O for full Hamiltonian evolution, and the O eta t is for the evolution with a discretized Hamiltonian. So we introduce some truncated Hamiltonian. For example, original OT is for the Hamiltonian for the whole system, and the OXLT means the Hamiltonian is truncated only in the region for the XL. For the outside region is just there's no Hamiltonian. It's just an identity. Yeah. So and then in this case, we can insert some factors in the difference to do the error estimation. The first and the second term can be bounded by the Lieber's amount, and we only need to estimate the last term. So the last term can be also bounded by a distance between the memory kernels. Yeah, then I will directly show the final result. Yeah, from this this Lieber's amount and also the bound for the memory kernel. So finally, we get something like this. So we can see for first term, it exponentially increased with the time t. So to cancel this term, to cancel the exponential increase for the time t, we need to choose L at least equals to time t plus something. Then this will exponentially decay with the system size or time. So we substitute this into the second term. Finally we get something like this. So which is proportional to d to the t to the d plus 1's power, and also some factor related to the eta. So here we use the O tilde to which emits a polylogarithmic factor of the 1 over eta, or nt over theta. Anyway, it's just an O1 factor. So we can see this is results, but nothing but replace the n with the t to the d's power in our previous results. This is somewhat not difficult to understand, because due to the Lieber's amount, only the sites in the vicinity of the region X can engage into the information propagation. So we truncate it, and in that case, the system size for a local observable X is actually t to the d's power. Only such amount of system size can engage into the information propagation due to the locality. Okay. Above is about the quantum simulation of non-Markovian dynamics. So is there any question?
I have a question. So you set up this problem of computing or estimating the local observable expectation values as a question of whether you can actually reduce the circuit complexity. I don't remember the exact expression for the full density matrix evolution, but is this in fact reduced compared to that?
Yeah, right, exactly. Yeah. So
Okay.
especially for a very large system and a short time evolution. Yeah, so this will be effective.
I have another question for this framework.
Yeah,
So
please.
is it suggesting that you can simulate the dynamics in a very short time for very large systems, only
Yeah.
with smaller system size, just like I can simulate some equals to 1,000 qubits with only equal to 50 if I limit the time, the evolution time with a very small range.
Yes, right.
Okay.
But I don't think, I mean, I think he's saying you only need to worry about 15 nearby. You still simulate the whole system, right?
But they also mentioned about the Hamiltonian truncation. So according to my understanding, maybe it means you really truncate the Hamiltonian.
Yeah, so simulation is still over the whole system,
Yeah.
but only the depth is reduced. Yeah. Yeah, thank you for your question. Yeah. So then we are going to move on to the quantum simulation of Markovian dynamics, namely the Lindbladian dynamics. So yeah, this returns back to the previous question. Yeah. So
I have another.
Running out of time,
Oh, please.
so maybe you need to, because we have, what is it? Right, so we are essentially out of time. Can you try to sort of
Oh, so,
move
sorry.
towards wrapping up and then take questions? Move towards wrapping up.
Sorry.
Yeah, because
Yeah.
we are out of time. We started like a little late,
Yeah.
but maybe if you
Oh.
can finish in 5 minutes and then take
Okay.
questions.
I will finish very quickly. Yeah, please. Question first. Yeah.
Oh,
No,
yeah.
finish first and then
Yeah. Well, questions at the end.
have to leave. Some people might have to leave, so finish first and then take questions.
Oh, okay. Yeah, so then, I will, finish quickly. Yeah, okay. So the central question, regarding to your, one of the previous question is, so why Lindbladian dynamics is very, difficult to simulate? Because the previous analysis felt that since the delta function cannot be expanded by the Legendre polynomials within the area delta, so we need we cannot truncate the Jmax in the previous analysis. So in this case, the Lindbladian simulation so violates the finiteness of the memory kernel. In that case, we cannot do the error bound or error estimation. So then we are going to consider to develop a completely different algorithm for the Lindbladian dynamics. So where the Lindbladian with only commuting jump operators. So the commuting jump operators, and also we firstly consider non-dissipative Lindblad equation. So where the jump operator here we introduce is a Hermitian operator. For example, like dephasing noise we mentioned, and also depolarizing noise. And we prove the following theorem. So if the jump operators are Hermitian and commuting, we can always construct an ensemble of unitary circuits by the trajectory of a Vienna process that can be efficiently sampled from classical computers, such that by taking the average of the Vienna process, we can approximate the quantum channel with the error delta, and especially the gate complexity as this, which is not the polynomial of NT over delta, but the polylog of NT over delta. Yeah, so we need to sample the classical Vienna process on the classical computer first, and then by using the classical Vienna process sampled, we design a circuit with the Vienna process. Yeah, then finally, we also assume the locality. Yeah, the locality is very important. I will basically skip the proof. I just show the Hamiltonian we design. The Hamiltonian we design is the system Hamiltonian, and also an interaction between system bus between system bus to simulate the system and interaction between system bus by a Gaussian noise here. So which satisfy this condition. Yeah. So then finally you can design the such a evolution. Yeah, so this is a previous conclusion by the Hastings paper. So it actually helps us to complete the proof. Also, we need the locality to prove this. So how to divide such a whole unitary circuit into some small chunks. Yeah, and for non-dissipative Lindblad equation is much easier than the dissipative Lindblad equation. So yeah, the most difficult part is this, because if the jump operator is non-Hermitian, the previously the unitary evolution or the Hamiltonian we construct also becomes a non-Hermitian one. So we cannot use the unitary evolution before. Then we need to resort to another method. A naive method is directly use the trotterization. Yes, just like this way for Lindbladian. Yeah, under Suzuki formula. But the problem is there's no inverse propagation for Lindbladian. When k equals to 2, so the middle one actually needs a inverse propagation for Lindbladian. So we can only make the k equals to 1. So yeah, this is the best we can do with the trotterization. And the gate complexity is given by this one. So where we only have p maximal p as 2. So we can do the better p here. So then how to realize the quantum simulation with nearly optimal algorithms? Until now, we don't know the answer. So we just try to improve the method before. So we use the dilated Hamiltonian by this one. Yeah, so still we need an ancilla qubit and the system. Then we design a joint Hamiltonian between the system and the ancilla qubit. And finally, we trace out the ancilla to get the evolution of the system density matrix. And our result can truncate the error up to the 4th order. Yeah, 1 order than before. So then the total gate complexity is given by this one. It's a little better than before. Yeah. The difficulty is, so if we want to construct the system the dilated Hamiltonian for the 1st order and the 2nd order, you can see somehow it's easy by using the system Hamiltonian and the jump operator. However, from the third order, when for this order, it's very difficult to move on. I will just show you the result. We work on this for a very long time. So the system, this is the system Hamiltonian, and also some interaction between the spin and the ancilla qubit. So at least we need the ancilla qubit of the 5 energy level. Then for many-body system, we just replace the J with JII plus 1 in the previous slide. So it's very complicated just to replace our J here with the JII plus 1. Compared with the previous results with the stochastic Schrödinger's equation. So their remaining error is something like this, and also gate complexity is this. So there is an additional n in the gate complexity. So for our case, it's this one. So if the n is very large, then our algorithm is better. I think it's the best algorithm. We now know. Okay, so then that's the end of the seminar. So let me make a summary. So in our work, we develop a nearly optimal algorithm for simulating non-Markovian dynamics with trotterization, discretization, and qubitization. We also develop a nearly optimal algorithm for simulating dynamics of local observables, whose complexity does not rely on the system size. Also, we for the Markovian Lindblad equation, we develop an optimal algorithm for simulating the non-dissipative Lindblad equation. Which is really an optimal one with the classical Vienna process. Finally, we develop an algorithm for simulating the dissipative Lindblad equation with a gate complexity. This one. But this is not the end. So our question is if we can firstly do the optimal algorithm for non-Markovian dynamics. Is it possible to use the Libra-Simon to really obtain an algorithm with the gate complexity like this? Second one is how to realize the optimal algorithm for the dissipative Markovian Lindblad equation. So is it possible to use the dilated Hamiltonian to simulate it to an arbitrary order for an arbitrary p? Finally, we want to investigate the optimal algorithm for simulating the dissipative particle system, especially bosonic or fermionic systems. Our theory is only applicable to the spin systems. Okay, that's all. Thank you very much. It's a little hard in hurrying.
Yeah, no worries. I have a question about, can you pull up your last slide? So you said that you are looking to get an optimal algorithm from non-Markovian dynamics. Where does that optimal bound even come from? Because I thought people didn't study non-Markovian open quantum systems before or come up with any bounds. So what are you benchmarking against?
So you mean benchmark this bound?
Yeah, where does that come from?
Oh, so it's from the closed quantum system. So for closed quantum system, so there's a theorem. So please check this. So for closed quantum system, this is the the optimal gate complexity for the simulation.
Is there any reason why that is what I should be comparing to? Because would it be possible for the non-Markovian case to even get that good? Like, how do you know? Is
Yeah,
there some
because
theorem that says, I don't know.
I
you
see.
can get-
Understand what I mean. Yeah. So the first reason is, so this theorem requires two conditions. One is the bounded norm for the local Hamiltonian. Yeah, the second condition is Libre's amount. And now we have both. So I guess if maybe we can get both, maybe we can get this. Yeah.
Okay. And then does all your calculations are done with a specific choice of like linear coupling or specific choice of like the Bath Hamiltonian? Or does your calculation depend on in an essential way on the particular setup, or like would I be able to use similar techniques to look at my other system with a different form of interaction? Or is there
Yeah,
like
that's a very
something
good question.
fundamental about your choice?
Yeah, that's a very good question. So we try to improve our result, but we found it's difficult. For example, if we don't use the Gaussian Hamiltonian, so this theorem cannot be guaranteed. So the probability can be arbitrarily large. Then right hand side it can even an O1 factor of the O1 order of the Boson number truncation D. So Gaussian bus is necessary. Yeah.
That makes
So-
maybe more sense, but with the linear coupling, that's also like, is that essential, for example? We need the coupling to take that
Yeah.
term.
So the linear coupling is essential for the discretization. Yeah.
Okay.
Yeah. So for here, we need to resemble it into the some discrete bosonic modes.
I
Yeah.
see.
If it's not a linear coupling, we cannot resemble it again. Yeah.
So maybe another way to say that is like, if I want to calculate a bound for my other system with a different coupling and different Bath form, it's gonna be really difficult. Like I have to basically start from scratch. Okay.
Exactly. So linear coupling and the Gaussian bus, they separate. Yeah, correspond to a difficulty. Yeah. Yeah.
Okay. All right. Well, thank you so much. It seems like people have some other places to be, but it was nice listening to your talk. Thank you so much.
Oh, is this the end of the talk? Oh, okay.
Yes.
Oh, people are leaving. Yeah. Okay. Yeah. Thank you very much. Yeah.
To have a very good sleep.
Okay. Yeah. Thank you for giving the talk at this time. Yes.
Yeah. Thank you very much. I'm going to sleep later. Yeah.
Okay, thank you.
Bye-bye.
Thank you very much.